Yeah, thank you very much for organizing this workshop. It's a great honor to open these talks, and right, and a lot has happened in this field, and so I'm looking forward to a lot of talks here. And it's also a great timing because it happens that in our group we also have quite a few yet unpublished results that I will be presenting today, and I'm very much looking forward to discussions with all of you to understand all these new things even better. Good. So what's great with alpha cold atoms is that we can do quantum simulations really of strongly correlated quantum systems, and as you know, experiments get more and more into the regime where it's really hard, where it is extremely hard to compute things, or where it's not possible anymore, and so we are starting to be able to explore things that can't really be computed. There is great progress, and in particular, a lot of the experiments are trying to realize models that are relevant to condensed matter physics, for example, that are relevant to actual materials and so on. And so but what has been largely missing so far is quantum simulations where you do quantum simulation of strongly correlated systems that have long-range interactions. Right. So in our optical lattice quantum simulation, we realize Hubbard models. And so what does that mean? That means atoms can tunnel from lattice side to lattice side, but we also have strong interaction, which makes the system strongly correlated. So if two particles are on the same side, this raises the on-site interaction energy U. And the question is, how can we extend this to really now also incorporate long-range interaction of various kinds, and depending of the kind of interaction, right, that is a very rich tuning now. Right? It can be long range. You can choose how the interaction should fall off, but there are additional things, like you can introduce anisotropy, for example, and that gives rise to a lot of new tuning knobs, to a lot of new tools. But how can it be done? Well, this first talk, why would I even want those terms? Because I mean, what was particularly nice about the quantum simulation of optical atoms is that they were pretty much an exact realization of the Hubbard model with pure on-site interaction, without all this annoying long-range stuff, right? But of course, well, that's a nice starting point. Of course, if you can now add long-range interaction in a controlled way, that's of course really what you want to do. One reason, for example, is if you want to do quantum simulations of actual condensed matter materials, or that are relevant to understanding actual materials. In actual materials, you always have some level of longer range interaction, right? You have Coulomb interaction. Typically, it's screened, so it's not that long range, but obviously, for any real condensed matter electronic system, that's always one of the first additional things you would want to consider, right? On top of that, oftentimes you write effective models where, for example, if you want to understand graphene, right, you can, if you look what the Wannier functions are, then you find that those Wannier functions overlap, and that means you have kind of like very strong, effective nearest neighbor interaction between those different lattice sites that are represented by these Wannier functions, and so you get these kind of extended models, and that's of course true in many condensed matter systems. But then, how about anisotropic interaction? Well, I mean, first of all, I would say that's not that common in condensed matter physics, so it's really a new knob, a new tool where we can construct very rich models beyond kind of what the interest is in condensed matter physics, except there are some interesting examples, like you can have anisotropic materials, you can have spin ice, for example, and there's a lot of exciting work on that, and so these would be interesting things one could realize in quantum simulations. More generally speaking, what does long-range interaction add to like a Hubbard Hamiltonian, to such kind of models that are relevant to condensed matter, for example? Well, the first thing is that in general, this long range, sometimes together with anisotropy and so on, and sometimes together with other short range, like for example, short range repulsive and long range attractive or so, this can give rise to structure, to rich structures of all kind of different kinds. But then it can also lead to frustration, right? And for example, if the system can't quite decide if it should arrange one way or the other, right? Then that gives you a new playground then for new states, for new quantum states that kind of create coherent superposition between the different possibilities locally. And typically, you get that geometric frustration, for example, on triangular lattice, but with long-range interaction, you can get that even on a square lattice, for example, where you would not have geometric frustration. And interesting states, for example, things like supersolids or so. And then more generally speaking, also, well, long-range interaction can create entanglement. Okay, but how can we create Hubbard-type models, kind of like itinerant models, where we have long-range interaction? Well, I mean, the obvious choice is molecules, right? This was pioneered, yeah, with David Jin and Jun Yi and Kangwen, the audience here. And there has been a lot of really exciting work, as you all know, over the years. And we'll hear some more in this talk, relevant to Hubbard physics and quantum gas microscopy. So recently, right, and Zoe will talk about that, I believe. Recently in the Seams group, there was a great breakthrough where it's now possible to also have a quantum gas microscope for molecules. And of course, once you see what you're doing, it's oftentimes much easier to then optimize things and really get things to the place where you want them. The phase-based entities are a challenge with molecules so far. Even after many, many years in this field, right, it wasn't really possible to get a really cold degenerate gas of molecules in a lattice, for example. But there are some very nice recent progress with like microwave shielding and techniques like that, where it is starting to become possible to evaporate. And so I think this will be really a very exciting direction to get more strongly correlated. And talking about strongly correlated, there are also mostly in tweezers, there are recent experiments where you can now see entanglement on the single particle level, kind of. So that is becoming really interesting, of course, right? The great thing is these molecules with electric dipole moment, they can be very strong with the dipole interaction, right? So that that should be great. But as I said, there are still a number of challenges to solve here. And also, it's not totally clear if you could ever make a Hubbard model where you, for example, have two molecules on the same side. The densities are very large, and so it remains to be seen if that is possible to actually have models like that without having too much loss. Well, what else can we do? Rydberg atoms, as you all know, there's a lot of exciting things going on in like spin or spin-like systems here on like Ising type systems, or recently also XY model, right? If you we also have anisotropic interaction, like for example, if you create superpositions between S and P-wave Rydberg states and things like that. So there is a lot of exciting things going on in the spin sector. Can we use Rydberg to have long-range interaction in a Hubbard, kind of in an itinerant model? Well, in principle, it's possible to do this via Rydberg dressing. And there were some nice experiments in Munich, for example. The problem is that it seems to be quite lossy. So it's not that clear how far it will be possible to push it. That said, I think they are getting some results now. So that's also something to look out for. And then you can play with light, right? There are lots of exciting experiments with Tillman and Ben, for example, where you use light in a cavity to create some kind of infinite range or long range potentials. The question here, I think, is for Hubbard physics again, is the system so isolated enough, or is that little bit of knowledge that you gain by losing photons, is that too much to create a coherent Hubbard physics? Right. And there are some very nice, so this is not related to optical lattices, of course, but there are some very nice condensed matter quantum simulation kind of where you have excitons and they start to form crystals, for example, or in twisted bilayer systems, also like crystalline states and so on. And these things also become more and more tunable so that you can also start calling those a quantum simulator, maybe, especially as you are starting to understand the model describing those systems better and better. Good. So those are a bunch of approaches, but the approach I want to talk about is using magnetic atoms. And this was, as you know, pioneered by Tilman Fau and Francesca Pellino and Ben Lev, who are here. And so there are lots of exciting experiments that I can't all mention here, but as you all know, you can get things like super solids and all kind of interesting physics. The question is, so can we use these magnetic dipole-dipole interaction to now build a system that has long-range interaction in a Hubbard model kind of setting? Well, the problem is, of course, that magnetic interaction has this C in the denominator, where it just means it's weak, right? So these atoms just aren't particularly strong magnets, right? And of course, here in these experiments, you always get kind of collective enhancement. If you have ensembles of atoms and they are oriented kind of the same way, then you get collective enhancement of these effects. But can we go into the strongly correlated regime where a single atom or single spin is now making all the difference in affecting the surrounding atoms in a strongly correlated sense? So that's the question. It doesn't look that good if you start thinking about it, right? Like for rubidium atoms, for example, in a normal optical lattice, the interaction is about 0.1 hertz, so we can always safely neglect that. Using the magnetic atoms, of course, you can boost that. So this could, for erbium, this could be like 4 hertz, for example. So becoming non-zero, right? But it's still very small. So what can we do? Well, the first thing is, of course, it's 1 over r to the third, so you can make the lattice spacing smaller. And if you have a green lattice at 532 nanometer with 266 nanometer spacing, then this dipole interaction for erbium is already 30 hertz if they are already the same way, or even 60 if they are head to tail kind of. So this is starting to become sizable, right? And in fact, Francesca Pellino was, of course, realizing that and did some very nice experiments where she created a Hubbard model where like in like 2D systems or a couple of 2D systems, you do have this nearest neighbor interaction. And in 2016, she already saw very nicely that you get a shift in your mod insulator transition first. So it's possible to introduce this term in the Hamiltonian. But the question I want to look into today is it possible to actually go into a regime where this term, this still very small term, like 30 hertz, where this now becomes the dominant part of the Hamiltonian? And it's larger than kinetic energy and is really driving the strongly correlated physics in the system. So that's the question I want to look into today. We built an erbium experiment. We started quite a number of years ago. There is a whole first generation of graduate students who did an amazing job to put together a very, very nice experiment, very well engineered. That's why it took a while, of course. And we also learned a lot from Francesca Falino, with whom we collaborated on how to make an erbium experiment like that. Here's the current team. I think they're all in the audience right now. Yeah. So the experiment is using a few tricks actually to get very fast Bose-Einstein condensation. Normally we are limited by cycle times of like once a minute or 2 shots a minute or so. But here it is actually possible by using narrow line cooling to reduce the cycle time by a lot. Like what we do is the mod is at 190 kilohertz line, but then we use a narrow 8 kilohertz line to cool the atoms optically quite close to degeneracy, and then we only need a fraction of a second of evaporation to get a cold degenerate gas. And that's huge because that means we have 1 picture per second or so, right? Which makes a big, big difference if you want to optimize things and if you want to take data. Now, we then started to build an optical lattice, and of course we want the lattice spacing to be as small as possible. So we chose green light, which makes an attractive lattice potential with the dipole interaction being 30 hertz roughly. But the question is, how can we turn this into a quantum gas microscope? Because it's very useful to image locally, right? But also for optimizing things. It helps so much that we can actually see what you're doing, essentially. But how did we do this? So this lattice spacing is only half as much as compared to other quantum gas microscopes. So you would need much better resolution, or scatter many more photons to get out of the signal to noise for like if the point spread function is there's a lot of overlap between point spread functions and so on. There are also some challenges how to cool erbium in a lattice. We have narrow lines, that's nice, but narrow line cooling is also slow in a lattice. So what we decided to do is a very different approach here that I will be showing you. So the idea is you have this very small lattice spacing, and then to image the atoms, we have a high-resolution microscopy. We have a high-resolution microscope with a numerical aperture of about 0.94 or so. For projecting, for diffraction-limited imaging, it's closer to 0.85. That's completely inside the microscope. And here's a picture, actually, Berlin is putting it into the apparatus, carefully inserting the microscope. So there's lots of things that I always sweep under the rug in talks like this, like are going on behind the scenes, of course. All theorists should know. And so the idea is then to use blue light through the microscope objective to catch the atoms, capture the atoms from that green standing wave. And then we can change the lattice spacing that is projected through the accordion to make it large, and then it's much easier to image the individual atoms. It's kind of like what you do in tweezers with that. So first, the reason why we don't do the science in this lattice is because it would have too much disorder. Right? There's always some light scattering in the objective, and what we learned from our first experiment where we project the lattice through the objective is there's always a 2% level disorder. So we have a very clean lattice here, and then we load the atoms to this, and then we increase the lattice. Here you can see how this looks like if we change in Fourier space the distance between the beams that go through the objective. We actually use a galvo mirror, the kind of mirrors that you find in a laser show, for example, to move these beams. Right? And after we do that and we have them well spaced, the cool thing is that we can do very simple imaging. We just shine resonant light onto the atoms for only about 5 microseconds. And then we scatter enough photons before the atoms fly away to very clearly tell us if we have an atom or not on a lattice. Right? And so the beauty is that that's very simple. This part is simple to be. I guess in my group, we often turn the complexity into the optics kind of part to make this accordion lattice. But the atomic physics here is actually quite simple, except there are actually some subtleties for this imaging. You have to quickly flash the illumination from 2 sides. So if you ever try something like that, talk to to us or to the Heidelberg group. Good. And so with all that, we can have a lattice. We can image in the lattice nicely. And so now let's try to do Hubble physics there. So we start with bosonic atoms here and in one spin state. And so we have tunneling. We have onset interaction. And now we have this 30 Hertz dipole-dipole interaction between neighboring in the lattice, which makes a long range interaction. That falls off like 1 over r cubed. And in addition, we can actually orient the dipoles arbitrarily just by changing our magnetic field, and the spins will follow that. So this interaction is 30 Hertz, right? Can we bring this into a regime where this is dominant? But in order to do that, right, we need to reduce our kinetic energy. And normally, right, your here, for example, also the onset interaction is about kilohertz. So normally, in strongly correlated systems, the interaction is something like a kilohertz, and then your tunneling is correspondingly smaller than that. Well, now our interaction is 30 Hertz, and our kinetic energy has to be smaller corresponding to that. So about like 5 Hertz, for example, right? Which means, well, like per second, the atoms don't tunnel all that many lattice sites anymore. Right? So is that possible? Is the question. Where does this get us? Well, if you can do it, the idea, so here our onset interaction U is actually large right now. We will also change that later. So we should be able to create Hubbard models with different population, but for now we just keep that large, which makes hardcore bosons. And that means that essentially we're in between the n equals 0 and n equals 1 mod lobes here at half filling. And if you change the ratio between tunneling and interaction here, or if you reduce the tunneling, then you're actually moving in between these 2 mod lobes in the superfluid regime. And theoretically, you would stay superfluid all the way for arbitrarily small tunneling. But now if you introduce this dipolar interaction, then all kind of interesting quantum phases are coming up in this regime here once your kinetic energy is smaller than the dipolar energy. And so we are always coming from a superfluid here, and then we do a quantum phase transition from a superfluid to a very strongly correlated regime, right, where you have a superposition of different, for example, spatial orientations or so, a very strongly correlated regime until at the very end, if T is very small, then we can understand it essentially classically like in a tight binding picture. There is quite a bit of nice theory here, but and I should in particular mention Barbara Capagrosso-Sanson, who has a series of papers of this, and predicting all kind of phases that can occur as the dipole interaction becomes dominant and as you now tune your dipoles. So last year we got the first signal where we can actually start seeing the correlation functions between the density in the lattice, and we can see if the dipoles are oriented this way. On the nearest neighbor sites, we already see some tendency to not have an atom next door, essentially. Or if you orient the spins the other way, we already saw some tendency that the atoms want to line up. And so we were quite happy to get into this regime where now the dipole interaction becomes sizable. But it was still a fairly daunting task because there are big challenges here, right? So first of all, if you think about it, disorder you have to control really well. Typically in our other experiments, we have disorder on the percent level sometimes. But here, well, the dipole interaction is 30 Hertz. The lattice depth is 200-ish kilohertz, right? 100 kilohertz. And so that means our disorder has to be 100 times smaller or so than in our other experiments. Otherwise, that would be the dominant kind of part, right? So you have 200 kilohertz lattice, but it has to be flat to within a few hertz. That's one challenge. And we've been working on that quite a bit. And luckily, of course, having the microscope is great because then you see your disorder, right? You see what's going on. Otherwise, it would just be a blind flight. And we had to pull lots of tricks, try different things. We tried incoherent light for whatever reason. It didn't work at all with Erbium. It just created totally weird. Thanks to Anantis in the audience also helping us with that. It created like weird heating rates that we don't understand at all. There's actually maybe some interesting physics there, so to be addressed in the future. We have a whole good objective to send a standing wave through there, but we were also a bit unlucky because the reflection at the window then hits the objective again, and that reflects back and focuses onto the atoms. But then even like the amount of such light that gets reflected and shown onto the atoms has to be far sub ppm to not cause disorder that is on that order of magnitude. So pretty crazy. But Lynn did a lot of work to the team to solve those problems and really reduce the disorder. And then the other question is, can we be adiabatic down to, like, can we reduce the tunneling adiabatically without causing heating, still be adiabatic, because we also need very cold temperatures at this range, right? But the good thing is, as we reduce tunneling, if we are adiabatic, then we can do it then we would adiabatically cool the atoms, and we would need to reach temperatures of a few hundred picokelvin, essentially. Well, after half a year of optimizing and playing with this and endless different attempts on how to send the beams to not create disorder and so on, we do have some nice results that I want to show you. So let's start with a situation where we have repulsion between the dipoles, right? If you have repulsive interaction, what do you expect? Well, I mean, to first order, the dominant thing is that you don't want other atoms on the neighboring side. So if you are at half filling, you would expect a checkerboard, and that's exactly what we find. So we can adiabatically start with a superfluid here, and then go into the strongly correlated regime, and we find a dipolar quantum solid here, and then ultimately in the atomic limit, you get kind of like a checkerboard kind of pattern. If we take the average of many pictures and calculate the correlation function, here's what how the correlation function looks on average, like the spin structure factor. And and if you take the Fourier transform of this, you get the spin structure factor, and this is the pi p's, of course. So yay, that actually works. Which I was never really sure when we built the experiment. Like, can we actually get it into this regime? Because it is daunting, but it turns out yes. If you do things right, if you don't move the cloud as you tune things, if you have your disorder low enough, and if your lifetime is long enough, you can just adiabatically go down at half filling all the way into the regime where the dipolar interaction is dominant, and is then giving you some really interesting physics. How about we orient the spins in this direction, right? So now head to tail, you have attraction, or here is diagram of the interaction, attractive interaction here, repulsive here. And so the ground state, a half filling, well, what could that be? But I like stripes. And in fact, that's what we see. So that works very nicely. Here's the correlation function again. This works even nicer because head to tail is like the attraction is twice as large as the repulsion. The interesting thing is it's actually a first order phase transition kind of between stripe and checkerboard, and we started to explore that. We don't have final data on this, but you can see very nicely that it actually turns out, to our surprise, we can even make a checkerboard and then change our double orientation. And we're still adiabatic enough to then turn the checkerboard into a stripe phase, for example, dynamically. We also are starting to see some kind of like onset that we simultaneously see stripe and checkerboard orders, right? Which is kind of interesting. And if you then look into more detail, we are getting some evidence that typically we have kind of like randomly oriented areas where it's more checkerboardy and where it's more stripey, kind of which we are now working on understanding in the context of like a microemulsion and just general things that you associate with first order phase transitions, and to really study this. And we started looking like for hysteresis, for example, in this transition. And so, yeah, I think there will be a lot of interesting physics to study related to first order phase transitions. Because as you know, typically most of the phase transition superfluid model is like second order. And so that's really nice to have these kind of examples. What happens if you tilt this by diagonally? Well, when we tried that, we got nice pictures like this. So there is some diagonal order. This is kind of, we were kind of surprised because this effect is not a nearest neighbor effect, right? Like the nearest neighbor interaction is repulsive for all of for all nearest neighbors equally. And you have, it's only beyond nearest neighbor, like the second nearest neighbor, that makes a difference here. But yet it seems to promote stripe phases until Alex started doing theory and calculated, no, wait a minute, that's actually not a ground state here. This is not what you expect. So what's going on? Well, then we tried and varied the ramp speed and found that, yes, indeed, what kind of phase we get, or we're getting metastable phases here. It depends on how quickly we ramp. If we ramp quite quickly, then the system can only communicate on a fairly short range length scale, and that means that you get an ordering vector that is fairly short. So for fairly fast ramps, we get like in K space here, we get large K vectors, and then as we ramp slower and slower, so this is from 15 milliseconds to being much more globally adiabatic, then we see that the ordering vector kind of gets like the period gets longer and longer. And actually, what actually happens here is that you kind of get phase separation. So for a finite size system, you have essentially a mod insulator in the center and empty around in a kind of a football shaped arrangement, right? We then started to look into this more quantitatively, and we now adiabatically ramp into different phases by orienting the dipole in the diagonal direction, but with different polar angles. Right? So what I showed you here, where the ground state is the space separated state, it points all the way here. But here I've shown for different angles what the polar interaction is like. So if it's it's pretty much in the plane, it looks more like this. But at certain angles, for example, the nearest neighbor completely vanishes, and you only have the next nearest neighbors, which are then again on a few hertz level only. Or look more like this. And it turns out that there is a whole rich phase diagram we calculated associated with this angle change, and you get different orders here, including some systems with frustration. So this one, for example, we expect to be super solid. We haven't looked into these kind of things yet, but so as a function of angle, even in the ground state, you do get different periods, and at the very end here, this blue part, this is essentially phase separated in the finite size system. And so what do we see? These are the orders kind of we then see if we ramp into these fairly adiabatically, the k vectors. And so here, this is the data where we plot the k vector diagonally, and you see as a function of angle how it changes here compared to some theory. So it's not a, so first of all physics is beyond nearest neighbor, right? But it's from this we could even conclude that it's beyond the diagonal, kind of it's really becoming more and more long range now, because here we compare to theory. The yellow plot is a theory which only assumes the nearest and next nearest neighbors. And then the green one is one where we have like 5 by 5 atoms. So it's really the longer range part of the interaction. And so this fits better than the other theory. So you can really see now that the physics is really driven by like long range anisotropic physics. Good, and then yeah, of course, you can have infinite fun by playing with these things. So with different angles, you get all kind of different patterns, and yeah, and so that's also called the theories. So tell us more what we should be looking into. We do have quite a few ideas. Obviously, super solid, right? For that, we mostly also want to now allow 2 particles on the side, right? To not have U large anymore. But in general, also, right? These quantum solids, I mean, so the kind of strong coupling limits are easy to understand intuitively, right? These orders, they're fairly classical, of course, right? And there, but the interesting thing is there are also some exact theorems understood about these kind of solids in the strong coupling limit, but nobody really knows how to now extend that into the quantum limit. So what happens if you start from this classical state, right, and really turn on quantum mechanics? And that's essentially exactly what we can do in the experiment, right? Because you get macroscopic superposition of different arrangements and things like that, and to study that would be quite interesting. Good. Yeah. Then let me get to the outlook. So one outlook. I mostly want to refer you to Vasilios, an undergrad working in our lab, who together with Alec and the rest of the team is starting to look into spin squeezing. So because what happens if you not only have the population now and the dipolar effect, but also the dipoles between the spins. So they realize a fermionic system with band insulator and so on. And then the idea is to use a clock state here, which is very magnetically insensitive, and have the dipole-dipole interaction to do spin squeezing. And it was proposed by Anna Maria Ray, and more recently also by Norman Yao, who found that there are some really interesting, he theorized that there is a connection between you get spin squeezing exactly if at that kind of like quenched temperature, you also would get magnetic ordering. And so it turns out with these finite range interactions, you should be able to do very nice spin squeezing. I don't have time to, so I refer you to the poster, but basically you can see if you see very nicely, if you move the spin vector up, it moves one way. If you move it down, it moves the other way. So that is twisting, right? So you can see that very nicely, and it looks exactly what we expect. And so now we are starting to actually do some spin squeezing where we have this shear motion, which turns our vector into an ellipse that we can sample. Yeah, but I'll talk to the team in the poster session if you would like to learn more about that. And with that, I would like to thank in particular all the members, so all the first generation team members, and Francesca, and the current team and the whole rest of the Greiner group very much for all this amazing work. And the funding agencies, of course, these experiments are never cheap. Okay, thank you very much.
Really beautiful results. Thanks for kicking off and giving us a nice overview of the field.
The quality of the government that you are training, because for example, you take a paper of Barbara, and you see that there are little ciliums of metastable state, and actually see have to anneal. I remember the person that I was going to get. Do you have to do something like this, or just go stay away?
I mean,
there are many.
Yeah, so we do have a finite. We have a finite number of excitations, right? So what the actual what you should mostly look at is are these kind of like average plots, right? So there are excitations, right? I mean, not every picture looks like that, right? This is a particularly nice one. But yes, I'm surprised. I'm also surprised how well it works.
You take for example the picture of Barbara, there are a lot of defects because simply because of the base of this part could move freely.
Yeah.
It's quite interesting.
Right, it's quite constrained, and yes, and exactly, yes,
It may have to do with the fact that you're coming in from the superfluid, right?
that helps, right? But of course, then you're in this really strongly correlated regime where you're starting, stripes are starting to form, except now it's still in the superposition of the stripe here and there and there and.
But if you went vertically, phase diagram from you change filling, then you probably will get done.
That would be interesting to study. So yeah, I think it certainly helps coming from the superfluid, right? Because in the superfluid, right, it's like even in the mod insulator, I was always surprised that you can get a pretty perfect mod insulator on a time scale that it takes one atom to tunnel to the neighboring site. Right? I think that here it's slower. It should be slower than that. Exactly, and that is, I agree that is a super interesting aspect. Still, I think having the superfluid may help, but we were also surprised how quickly we can go, for example, from a checkerboard to a stripe phase. I mean, again, not the zero entropy, right? So, it's not perfectly adiabatic, right? But I was surprised. Like I would have thought if we reduce our tunneling to a few hertz, right? I could see how we kind of can go down there because not much changes anymore in the end when tunneling is small. But it turns out even at that small tunneling, 5 hertz, we can now change the type of orientation and go from a stripe order to a checkerboard back and forth on a surprisingly fast time scale. To me, surprising.
Yeah. So to stay on the schedule, maybe we'll. Hey, Marcus, but we have plenty of time during coffee and so forth.
That's good.
Thank you.
Sorry.